Hey, good day, everyone. Today we'll be discussing the second part of our section properties, which is all about uh, solution by composite method. So the solution by composite method. So let me share my screen, my entire screen. Okay, so I am now sharing my screen. So actually, the introduction for this topic. Okay, let me make this as a slideshow. Okay, wait. Okay, good screen. Okay, so part of the introduction that we had for section properties, uh, of course, I already uploaded this course material. If you read further beyond the introduction, uh, you will see that we already have a reference, or we already had the reference for the topic. So if we recall, we concentrated on the formulas used for the integration, even for the areas, for the centroid, and well, the center of gravity, if mass, and moment of inertia. Right? Now, of course, there's also the parallel axis Schurer, or the transfer formula, or the squeeze Schurer. Okay? Now, there's a part on the formulas included in this course material, which is applicable for the composite method. Okay, so of course, as you know, the symbol of integral or the integral sign looks like an elongated S. So it's an old symbol which used to represent summation. Okay, of course, nowadays we are using the symbol, the sigma symbol for the summation or to represent summation. But before we are using the elongated S. So it means, remember I told you one of the reason why integration was invented is to approximate areas. So without the limits, uh, to solve for an area of a regular cross section, we divide it into thin rectangular elements. So why rectangular elements? Because rectangle is the easiest area to recall. So regardless of how many rectangular elements we're going to have to solve for that irregular cross-sectional area, we just simply solve each area of those rectangular elements, then we add them. That's the summation. Okay? So it basically means if you check the formulas for the area centroid, the integral symbols will be replaced by the summation symbol. Okay? Even for the area, for the centroid, center of gravity, and for the moment of inertia. As you can see, uh, all integral symbols are replaced by summation symbols. And so that's the difference. So of course, this time we'll be using the formulas that we have derived. Although uh, this is where the the presence of the analysis of our problem, where the dimensions of the centroid or the position of centroid from the reference axis uh, will be passively placed, not on its sides or on the basis where we use as reference when we derive their formulas. It can be farther than the given base or given sides. So what I mean is, for example, we derive the formula, let's say the rectangle, okay, where we assume that assuming this is a perfect rectangle, the sides coincides with the x and y axis. So when we measure the centroid, Um, we measure the exact centroid or position because the sides are aligned with the or collinear with the axis. Let us say, for example, since we already know the formula of the rectangle, so if I ask you to solve for the, let us say, centroid or the distance of the centroid of this rectangle, let's say above the x-axis. So it's not enough that you apply the formula that we derived. So when we derive the formula, assuming this is h, this is b, we know that the vertical centroid is one half of the h. So using this formula is not enough to determine how high the position of the centroid above the x, because you need to add the h over 2, which is coming from the centroid and the bottom side of this rectangle, and this one, whatever the height of that. So we'll be having the total height of the centroid from its position towards x. So it's the addition of the formula that we derived plus whatever the gap we had from the bottom side up to the reference axis. So same thing with the horizontal centroid. So this is our x bar, and we know that this is one half of the base. So when you will be asked what's the position of the centroid of this rectangular cross section from the y-axis, if this is our figure, so after you apply the formula in getting the centroid of the rectangle towards its base or its sides, we need to add how far is this. Okay, so you add this to the centroid, then you will have the total distance of the centroid of the centroid of this cross section. So in this case, it's rectangle towards the y-axis. So that's what we're doing. So there's a possibility that this time the figure is, well, will be not aligned with the references that we use when we derive the formula. Okay? Especially if we're doing composite section. So in composite section, it's actually a mixture of these shapes that we use or we derive. So the idea is, of course, we have to recall the formula for the exact shapes. Then we need to add, especially the moment arcs or the radius of variation. No? If the cross section is drawn like that, okay. But first things first, no, let me clear this one. Before we proceed in solving problems, of course, in the problem solving, you will know the process, no? Uh, Although we already have four examples, no, in the solution of section properties by integration. Um, just to verify uh, if you know how to work on with Wallis formula, because I asked the other sections, uh, if not all of you, on majority of you weren't able to reach the topic Wallis formula. So that's why I asked you to make a research on the Wallis formula and give examples so that you will know how to use the Wallis formula, when and how to use. Okay? When will be Wallis formula is applicable? So whenever Wallis formula is applicable, it will shorten the process of the solution, because instead of processing the integral by the process of integration, we just solve it using the Wallis formula. Okay, so there will be no integration process anymore because the answer or the formula was derived using the Wallis formula integration. I mean the integration process. Okay, so I use the Wallis formula when I derive the quarter circle. If you watch my pre-recorded videos, so you will, uh, if you watch it, then you have seen uh, the the well comparisons of the solutions on how you prove the section property of a quarter circle. So I basically solve it in different ways applicable to that problem. Uh, if you will recall, I solved let's say the area, no, first by the traditional method. So when we try to replace the variable so that we will concentrate on the other variable, it turns out that there are more than one or more than two variables. That is why there's a need for us to extract a triangle since amongst those three unknown variables, there's always a constant letter or constant parameter, which is the radius. Okay? So I use a trigonometric substitution based on the right triangle form on the projection of the radius and the element measured above the x if it's horizontal or measured from the y-axis if it's vertical. Okay? So it means we produce a right triangle, and then from the right triangle, we determine the relationship of the variables with respect to the constant angle, I know, constant radius, which happens to be the hypotenuse, and the angle. So even the angle is variable since if your element will be chosen near to the y-axis, let's say you're using a vertical element, the angle is larger. So if it's farther from the y-axis, then the angle becomes smaller. So same thing if we're using the horizontal element, the farther the element from the x-axis, the smaller the angle. Okay. So we have three variables, one constant. Okay. So by trigonometric substitution, we were able to reduce the number of unknowns. We introduced the theta to replace x and y. Okay, so that's what we did. Now, of course, the first solution is after you make use of the trigonometric substitution, then you integrate it. So in that case, the answer will have theta. The first choice to complete the solution is to return to its original variable. So from theta or any angle used in the trigonometric substitution, we return to the original variable, so that we should be able to use the limits. So remember, there is a limit, or there are limits to be used, so that we can find the final answer. Since, if, let's say, for example, I'm using a vertical element, limits will be based on the x-axis, okay? Since differential of x. So I mean to say, the original limits is only applicable for the x because we're using differential of x or yung function of x. So it will not be applicable in the new symbol, which is theta. So that's why the first option is if you want to make use of the given limits, we return from that new variable to the original variables, okay, between x and y. So that's the first method. That's the traditional method. Second, there is what we call change of limits when change the variables. So since in order for us to evaluate or to prove the quarter circle, there was a need for us to introduce the trigonometric substitution. So if in the first uh, choice on how you complete the solution is to return from the new variable to because of the limits, this time we can change the limit which will be applicable to the new variable and which is the equivalent from the new function. So what I mean, let's say for example for differential x, we have r and 0. So from the angle, I mean the triangle form to determine the relation between x theta r, y theta r, we use what the relation which will show the relation between x and theta. So by solving theta there, which will be arc cosine, you will see that will be x over r. So if x will be replaced by the upper limit in the original variable, which is r, you will have r over r, or basically r over r is 1. So you solve what is the equivalent of r cosine 1, you will get there 0 degree, but you have to convert it to radian so that if your answer doesn't have a trigonometric function, then you need to use the radian measurement. Okay? So that's the idea for the limits. So the equivalent of the upper limit, which is r, in the new variable is 0. Now, what will be the equivalent of the lower limit 0? So in the relationship between x and arc cosine theta over r, you replace, I mean, sorry, x over r, you replace x by 0. So 0 over r is 0. Okay? So you solve what is the arc cosine or inverse cosine of 0, you will get their 90 degrees. Then you convert it to radians, you will have pi over 2. Okay? So that's the second option. You introduce new limits so that you do not need to return to the original variable. You use the new variables, which is theta, and apply the necessary or applicable limits, which is 0 and pi over 2. Okay? Now, the third solution is the use of Wallis formula. So as you can see, before you can even use the Wallis formula, we have to check if it's applicable. How do you know if it's applicable? It should follow the format of the integrand. Okay, so according to the rule, in order for us to determine the given limits or the differential or the definite integral, the limit should have pi over 2 and 0. Okay, that's the first requirement. And we should have sine of an angle raised to any positive exponent m and cosine any positive exponent n. Okay, so in the case of the counter circle, since the lower limit is pi over 2, the upper limit is 0, we interchange their position by a new property, okay, that allows us to exchange the position of the limits and producing the same result by multiplying the whole integrand by negative. So that's why I was able to interchange the position of the limits. Originally, pi over 2 is the lower limit, the higher limit is 0. So I interchange their position. Pi over 2 now is the upper limit, 0 is the lower, provided I multiply negative sign on the whole equation. Okay? So if it's applicable, there's a formula that we're going to follow. No? Uh, so if you watch the pre-recorded video for the quarter circuit and you have also your example for the Walls formula, you will understand, well, I have to assume that you know the process. Okay? Now to verify that, let us have another example using integration before we jump in with the example for composite. This time, let's say we'll be proving the section properties. So prove, uh, let me arrange that. Prove the section properties, okay, of a given quarter ellipse, okay, without any restriction. No? We just need to prove the section properties. So that will be the area, the position of the centroids, x bar and y bar, and the moment ko na siya about the centroidal x and y axis. So that's the axis of x and the axis of y. So we make use of this of the same line of reasoning as what we used in the earlier cross sections that we have as our example problem. What I mean is choosing the first quadrant to make sure that all coordinates will be positive and aligning the sides of the quarter ellipse, similar in what we did in quarter circle. Okay, so quarter circle, uh, assuming this is straight, this is our quarter circle. So just like the formula of the circle, actually they have similarities. No, um, the formula of the circle is geometry, not integration. You will see that it came from the formula of an ellipse, or in this case, it's quarter ellipse. Okay, so the area of the whole ellipse is pi AB. So quarter ellipse, you simply divide it by 4. Okay, the small letter A stands for the semi-major length, and the small letter B stands for semi-minor length. So if you already encountered the figure of the ellipse, you will know that there are two sides. Unlike circle, they have the same sides, which are diameters. In this case, the major length is more longer than the minor length. Okay? I mean the semi. So therefore, the semi-major length, which is one half of the major length, and the semi-minor length, which is one half of the minor length. Okay. Uh, you will check. You will see that the semi-major length is greater than the semi-minor length always. No? So in circle, if you replace A and B, since they're the same, they are both equal to R. If we're solving a quarter circle or circle, then you will have pi r times r over 4. Or multiply the r times r, that's the r squared. That's why you have pi r squared over 4. So you prove the identity using geometry. No? So this is what we're going to prove, no, as our last example before we jump in with the composite method. Okay? So the idea is, this is our y-axis. No? So we're trying to prove this area of the ellipse. Okay? So the x bar in the circle, actually they are the same because they are perfect in symmetry. So x bar is equal to y bar. And as you recall, uh, x bar and y bar for the circle is equal to 4r over 3 pi. Okay? But in the ellipse, the x bar will be different from y bar because x bar will be based from the semi-major length and y bar will be based from the semi-minor length. So we already know that x bar, if we use the centroid, if we use a quarter circle or half circle, is equal to 4r over 3 pi. Same thing with the y bar. If we're talking of a circle, but in here, uh, the r is a and the other r is b. So basically, it means in the x bar, we replace r by a. It's now 4a over 3 pi. For y bar, we replace r by b, 4b over 3 pi. So same line of reasoning will be used if we try to prove the axis of x and axis of y. But I will allow you to do that. No, you just follow what you did in the circle. Of course, we need to make use of the transfer formula. Okay, so if I want to prove this one, assuming I'll be using a vertical element, let us say. Okay, this is a vertical element. This is the height is y, and this is differential of x, and the distance is x. Mean to say, I can prove the area, I can prove the x bar. You have to do you have to use the horizontal element to prove the y bar and the area, of course. And of course, mine will be the axis of x, yours will be the axis of y. Sorry, yours will be the axis of x, mine will be the axis of y. Okay? Making use of the transfer formula. So just like what we did in the circle, okay? So this is represented by r, if you recall. And the angle of the inclination, if that's a perfect triangle, that happens to be the right triangle. No? So again, the good thing about integration by plane areas, we disregard the original area. So we discard the quarter ellipse and we concentrate on the area of the element. So if it's vertical, area is equal to the integral of y differential of x, okay? Where the upper limit will be based on the x, okay? So that will be what? So instead of r and 0, you will place there a and 0, okay? So then we replace y and x in terms of a new variable so that we will have a single variable and one constant. That is by utilizing the right triangle form. This is the element, this is y. The distance of the element from the y-axis is x, this is theta, and this is r. And we already derived the formula. X theta r, that is r cosine theta. For y, that is r sine theta. Okay? So, but in the ellipse, r is from 0 to a. So this will be a. So replace r by a. And we replace r here in the vertical position by b sine theta. And we need to solve for the differential of the x. So what's the differential of that? That is a times the differential of cosine theta, which is negative sine theta differential of theta. Substitute in this limit. A now is equal to integral of y is b sine theta. Differential of x, 1, let's simplify. That's negative a sine theta differential theta. So that will be negative a sine theta differential of theta. Okay, then we simplify. Obviously, we have to trans or put or write the constants together with the negative sign outside the integral sign. Negative AB. Okay, sine times sine, we have sine squared theta. Differential of theta. Now, how about the limits, no? So the limits for x is a and 0, but that is only applicable for x. We need to have the what is applicable of the limits from the for the new variable, no? So since we make use of the limits for x, we need to use what the relationship or the expression which shows the relationship between x and theta. So that is x is equal to a cosine theta. So we make use of this, solve for cosine theta, then solve for theta, which is inverse cosine. Arc cosine x over a. So if I replace x here by the upper limit, which is a. So what do we do? Theta is equal to arc cosine a over a. We replace x by a. So definitely this is 1. So if we ask what's the integral of arc cosine 1, I mean what is the arc cosine 1? That will give you a 0 degree value. Of course, we need to convert it to radians just to be sure. 0 times pi over 180, that is still 0. Okay? That is for the upper limit. It means the equivalent upper limit, if we use theta for a, is 0. Okay? Now, for the lower limit, we replace uh, x by 0. That's the lower limit in here. No? So theta now is equal to arc cosine 0 over a. So 0 divided by any number is 0. So what will be the arc cosine of 0? You will get there 90 degrees, or in radian measurement, that is pi over 2. So it means our lower limit is pi over 2. Okay? Now, this is this looks like an integral applicable or solvable using the Wallace formula, except that the limits are not the same. I mean, the pi over 2 is below, or the lower limit, 0 is the upper limit. So in order for us to interchange their position, what we need to do is multiply negative signs in the whole integral expression. So we multiply the integral sign, I have the negative sign. So we have negative AB. We interchange the position of the limits, sine squared theta, differential of theta. Then we make it positive. So outside we have AB times pi over 2 and 0, sine squared different theta, differential theta. So at this point, you have to choose. Do you want the first method, where you return to its original variable? The second method, we introduce a new limit without going back to the new variable. And the third, changing the limits and the variable allows us to use the third method, which is the Wallace formula. So if it's applicable, no? So again, let me write the integrand. So what is left is that the area is equal to AB integral of pi over 2 and 0 sine squared theta differential of theta. It means whatever the integral of this using Wallace formula, just simply multiplied by AB. Now in the Wallace formula, we need to follow this format. Okay? Where the condition of m, which is the exponent of sine, and n, which is the exponent of cosine, should be positive. Okay? So there are conditions on the formula that we're going to use, no? So first is the first factor. So you might say, if this is the given, there's no cosine here. So we cannot use the Wallace formula. Yes, we can use. And so what all we have to do is rewrite this. So what we don't have is, so we have sine. What we don't have is the cosine. But if you place there cosine of x raised to 0, differential of x, then you will see that now the Wallace formula is applicable. Only the exponent of cosine is 0. Doesn't matter, no? So the first thing that we're going to do is get the factors of the sine or the m. So for the first factor, uh, whatever the exponent of the sine will be subtracted by 1. That's the factor. Then you subtract, whatever the result, subtract by 2, or by formula, that is minus 3. Then minus 5, then so on and so forth until you reach the factor of 2 or 1. So that's the factor for the exponent of sine. So same thing that what we're going to do with the exponent of cosine, but this time we'll be using n, okay? Until you reach the factor of 2 or 1. Okay? The denominator, the first factor is we add the exponent of the sine and the cosine. Then, whatever the result, for the next factor, we basically subtract by 2. So, by 2 ng by 2 until we reach the factor of 2 or 1. So, to complete all of this, uh, all of that, I mean, to complete the Wallace formula, all of this will be multiplied by by an alpha, okay? So, a multiplier alpha. So, alpha now is conditional, no? So, if your exponent, if both exponent, both m and n are even, then alpha is equal to pi over 2. But if one of the exponents, so either m or n is odd, then our alpha becomes 1 only. Okay? So that's what you need to do. That's what you need to apply if we intend to solve this, so that we can solve the area. So you can see that the exponent of sine is 2, the exponent of cosine is 0. So exemption to the rule of factoring. Having factors like this, so there is an exemption or there are exemptions to the value of the exponent. If the exponent is 0 or 1, okay, you replace the entire factoring. Huwag na itong gamitin at ipalit na lang dyan or we replace it by 1. So that's the idea, no? So again, what we're going to do, if uh, the exponent of either m or the sine or n or the exponent of cosine is equal to 0 or 1, that's the lowest exponent that we can have to apply the power formula. So instead, we are going to replace the factoring, the one that we use or what we'll be using, like this one, by a factor of 1 only, and you're done. No? So what's the reason? What's the reason? Let us say your exponent is 0. So if you subtract it by 1, so you will have 0 minus 1. The next factor will be subtracted by 3. So you will have 0 minus 3, then so on and so forth. Since it is negative, the numerator or the denominator becomes larger only. Okay? Uh, it means the value becomes larger, but the sign, okay, becomes negative. So same thing if your exponent is negative. So you must subtract 1, subtract 3. So it's an infinite process. So what we're going to do, if your exponent, either m or n, is equivalent to 0 or 1, replace the factoring by 1 only. But in the denominator, you need to add the exponent. So just like this one, uh, I'll be using this space. Okay. Uh, so AB, that's the multiplier, multiplied, I mean, that's the constant, multiplied to whatever the integral of this using Wallis formula. So AB times the Wallis formula. Numerator, we subtract the exponent of n by 1. So this becomes 1. So since we already reached the 1 factor or the factor with this 1, we stop the factoring because that's the ending. No? Now for the exponent of cosine or yung n equals 0, that's where the condition that you're going to disregard the process of factoring and simply replace everything by 1. Okay? Now, for the denominator, we add the original exponent. So, first term is 2 plus 0 or 2. But we already have the note or condition there. If you reach 2 or 1, then you're done with the factoring. Just like what we had, no? 2 plus 0 is already 2. So, we do not need to factor anymore. So, as is. Now, for alpha, since 2 and 0 may be considered as even, okay, or both are even, then alpha becomes pi over 2. So you simplify whatever we have in the bracket or inside the bracket. That will be multiplied by AB. So AB times, this is pi over 4. So simplify, your area now is pi A over 4. Okay, so I have proven the area of the ellipse to be really pi AB over 4. So it means you have the area of the ellipse divided by 4. That's the area of the quadrant. Okay. So what's next? Let's prove the y bar. So since I'm using the vertical element, I'll be proving the x bar instead. So in the x bar, same as what we did on the other cross sections. Solving the centroid or the position of the centroid, whether it's x bar or y bar, will require us to use the variance theorem. So remember the variance theorem. A resultant area multiplied by x bar, because I'm using the vertical element, is equal to the area portion, so that's the differential area, multiplied by the distance of that area towards the y-axis. Okay? And of course, we transfer, okay, or transpose this area on the right side. That will give us the formula for the x bar. Okay, so how do we do this? So since we're repeating the process, uh, for example, we already defined what is differential of A. Since I'm using a vertical element, okay, sorry. So I'm using the vertical element. Okay, so let's check, no? Oh, as you can see, I'm using the vertical element. So it means the okay. I already know what's the area of the element. Okay, this one is y differential of x with the same limit as r and 0. Now we are going to replace the x and y in the differential of x. Uh, x is equal to this one, a cosine theta. So we replace x. This becomes what's that? A cosine theta y by um, b. So x cosine theta, so b sine theta, and the differential of x, that is, so in here differential of x, this one, negative a sine theta differential of theta. Okay, so that will be negative a sine theta differential of theta, then all over a. Okay, so we place, then how about the limit? Uh, Originally, we change the limits to what is applicable for theta. Upper limit is 0, pi over 2 is the lower limit. Since we're going to factor the a, the b, and the negative a, we multiply everything by negative sign so that we can switch the position of the upper and lower limit. Instead of having negative, we'll be having a positive. A squared b integral pi over 2 now is upper limit, 0 is lower limit. Then we will have sine squared theta cosine theta differential of theta. So if I intend to use the Wallace formula, I have to determine what is the value of m, the value of n. You cannot see any value, that's 1. Okay. Then alpha, since one of the exponent is odd, alpha is equal to 1. So let's simplify. A squared b times the Wallace formula. So for the exponent of m, subtract it by 1, that's the first factor. Since it's 1 already, we're done with the factors of n. For the factors of n, since n is equal to 1, so we also apply what we applied earlier on the 0 exponent. We replace the factoring by 1 also. So we replace this by 1. Denominator, we add the exponent as the first factor, 2 plus 1. And the second is 1. Okay? Now, since one of the exponent is odd, alpha is equivalent to 1, then whatever the result will be multiplied to a squared b. Okay? So, again, there's a divisor area. Okay, so we're going to divide all of that by the derived area. So this is 1/3 times a squared b. So our numerator is a squared b over 3. Now, we replace area to the value of the area that we have solved, which is equal to pi ab over 4. Okay, that's the formula of the area. So since it's in denominator, fraction, we proceed to multiplication, but we interchange the position of the numerator and denominator, vice versa. The reciprocal. Okay, so the area is pi b over 4. Therefore, the so that's on the bottom, no? So reciprocal, it should be 4 over pi over a over b. Okay, then we cancel a squared in a and b and b. So what's left for our x bar? X bar is equal to 4a over 3 pi. Okay, which is what we try to solve or prove earlier. You will see it in here that the x bar is equal to 4a over 3 pi. The y bar is 4b over 3 pi. Since we solve for the y bar, we need to use, for the x bar, it should be x4a over 3 pi. Okay, so that's the x bar. But for the remaining sample, I mean, for the remaining section property, which is I sub x or I sub y, I'm going to assign it to everyone. Just continue the solution. The remaining section property will be the I sub x and the I sub y. Now, we proceed with our lecture, this composite method. And I already mentioned uh, what will what we need to do to change the original formula of integration to summation. So all formulas we use in the integration will also be used. Okay. I mean, all formulas, yes, the will also be used in the composite, except that we replace the integral symbol by summation. That's what we need to do. So let's now solve a particular problem where we can apply concept, not this one. So let me just snip this so that we will have our first sample problem. Okay. So locate the centroid y bar of the composite area shown and determine the moment of inertia of this area about the centroidal x-axis. So you can see the axis there. We have the original x and y. The x prime will be the centroidal x-axis. Now, in case you're wondering, I mean, uh, in true practice, we can even remove the y-axis because we know the reference, which should be above the x-axis. So it doesn't matter where you place your y-axis, no? Because it won't change a thing. What we're going to solve is the vertical centroid, not the horizontal. So whether you draw it in the first quadrant, the second, third, or fourth, or just like what the problem did, where it placed the y-axis on the center line. So it's easier to measure the centroid, no? If we are required to solve for the horizontal centroid. But in the problem, it's the vertical centroid. You can see it in the figure, no? So if I have to expect, based from the figure, since I have a 2 inches width here, and the centroidal axis is below the 2 inches, so our answer for y bar is basically less than 2 inches. Okay, so that would be for the y bar. For the moment of inertia about centroidal x, of course, there are things that we need. The IXX, but in this case, it's a summation. So first phase of transfer formula, the second phase, no? So that's the phase of the procedure, no? So problem will normally, or the figure will normally tell you how many times you're going to divide the figure. Okay? Sometimes it's not, but normally it is. You will know, no? So since we have, or we can have three pieces, no, of this original figure. Mean to say we can divide the whole thing by three different areas, and obviously all areas are rectangle. Okay, but of course you need to strategize. What division of triangle or rectangle you can use, no? So there are four ways actually five, no? But let's concentrate first at four ways on how you intend to uh, divide the whole cross section. So let me just skip this so that I can show you properly. Okay. So how to divide the figure. So we'll be having figures. Okay. So out of the four or five, uh, of course, some of you will try to solve this by dividing the whole thing. If you choose to have this rectangle, okay, and we will have two identical rectangles, no? So if I use this as my first, second, and third part, that is our first, uh, well, the initial idea that we have on how you're going to divide this cross section in series of rectangles. So there are three, and that's one way of dividing the cross section. No? The other way is instead of horizontal, I'm sorry, let us continue this. So assuming this is straight, right? So straight, let me arrange that. How are we going to make this straight? Okay, that is assuming that is straight. So I have this as my first and second element, which are identical. This is now my third. Okay. Of course, the other is combination of that. No. Probably some of you will go this or will do that for this straight and this one. Right. So regardless on how many ways or what's the manner of how you're going to divide the whole cross section into rectangular parts, you have three parts. Okay. And you either choose the first or the second. No? So if I give you a hint, it's easier to divide the whole thing by the second. This one. You use this one, so when you solve it, it's much easier. Okay, but I will allow you to solve that using this one. I'll be solving it using the other division. No, so instead of this, so again, I'll be asking you to solve this using this. But for me, I'll be using. So let me just and delete and erase. I'll be dividing it like this. This is my first part, second part, third part. Okay, and obviously my first and the second parts are identical. Since I cut the original 5 inches by 2 inches, this is now 3. Okay, so the whole thing is 6 inches, and of course the base is 1 inch. So regardless whether your rectangle is drawn vertically like this or horizontally like this, make sure that you label them similar on how we labeled our proving. No? where B will be the base, H will be the height. So whether it's vertically drawn or horizontally drawn, you will have the same wavelength. Okay? So if you do it on the other solution, you will see which is more convenient, this one or the other one. No? Now, since we'll be having multiple solutions because of the need to use the transfer formula later, and it's it's combination of products of the area, the distance, and so on and so forth. When you say you will have a lot of units, no, in your solution. So to make your solution organized and easier and more simplified, I suggest that you use table or tabulate your solution. Similar in what you're doing in your aerodynamics when you were asked to plot or to construct a table. Uh, by including the unit of the column, so it means to say if you put their numbers, it's understood that all entries on the column will have the unit, okay, of the table or of the column. Okay. So for example, all data will be in inches. So instead of writing 4 inches, 5 inches, 2 inches, you will just write 4, 5, 2. So the numerical part. So when you say by tabulation, it involves rows and columns. Although I'll not be writing any more the lines, understood that we're talking of rows and columns. So for my solution, my first part will be my column 1. This is my decision or our decision in this case on how are we going to divide the original cross section. So we decided to divide it by 3 parts. Okay, that's the first column. The second column is the areas of each part. Now introduce a new variable. Since the dimensions are all measured in inches, definitely the area should be in square inch or square inches. Okay? So we already divided the parts. Part 1 and 2 are identical, so you just need to solve it once. So it's like asking us what's the area of part 1. So base times height. So we already know the formula for the area. It is base times height, regardless of the figure, no? So vertical base will be 1 inch, height will be 3 inches. So formula of the area base times height. So 3 times what? So that is 3. Same thing with the next part. So for the bottom part, which is part 3, you have 6, 3, and 3. So 6 times the height of 2 or 12. Then at the bottom, we add all of that. You will get 6 plus 12, that's 18. So we all know that that's 18 square inches. Okay? So that's the second part. The third part is we determine the position of the centroid above the axis. Okay? So we already know the formula of centroid of rectangle. It is always, so vertical, it is always 1/2 of the height. Okay? But since our reference will be the x-axis, for example, the parts 1 and 2, assuming this is the parts 1 and 2, no? And this is the x-axis. So we all know that from the centroid towards its base, that's 1/2 of the height. But we need to add the gap from h over 2 so that we can measure the whole distance of the centroid above the x-axis. So in this case, since the height is 3, we divide it by 2, that's 1.5. Then you add the gap, which is 2.5. That will be your total centroid of parts 1 and 2. So that will be, instead of 1.5 only, that should be 3.5. Okay? Now, for the third part, which is the part, this part, the bottom part, it is already above the x. So we do not need to add anything. So we basically divide it by 2, then that's the centroid. So it's 2 inches divided by that will give us 1. Okay? Now, next, the fourth column is actually the product. So let me write the column in here. It's no longer the product of the second and the third. So it means we multiply the area and the y. So basically, we are also multiplying their unit. So it becomes cubic inch. So let's use a calculator. So we have 3 times 3.5. Okay, so equals 10.5. Okay, so that's the 10.5. So the first and the second parts, second and third, first and second part, that's 10.5. Now for the third part, that's 12 times 1. Basically, that's 12. Then we add all the parts. We will have area times area, uh, summation of the area and the y. So basically, we just add all of this. We will get, what's that? 10.5 plus 10.5, that's 21 plus 12, so that's 33. Okay? So before we continue our table, bear in mind that we need to solve for the y bar, where I already shown what's the formula. Okay? So you will see there y bar is equal to summation of the product of the area and y all over the summation of the area. So we already have the summation of the area, and we already have the summation of the product of the area y. So we pause and solve first the y bar since it's part of the requirement. So according to the formula, y bar is equal to the summation of the product of the area and y divided by summation of the area. So the summation of the product of the area and y is 33 cubic inch. That's the unit divided by the area 18 inch squared. Cancel. That gives us the value of y bar. So let us solve. That is 33 over 18. So we will get 1.83. So that is 1.83 inches above x-axis. Okay, let's try to underline that. So now we can continue our table. So remember, we are in our fourth column. Sorry, it's a little bit, so how do I say it? It's not proper, no? It should have been a proper table. Uh, what if we rewrite everything? Let me see if I can cut this. Is it easier? Let me see, no? If I can cut this. Allow me to cut this. Okay. And let me use it on the next column, in the next frame. Okay, so pwede, no? So, okay, so let me just complete this one. Remember, we already solved the area. The fourth column, we have the area y, inch cube, 10.5, 10.5, and we have 12. So this one, this is 33. Then we solve for the y bar. So to continue, going back on the next step that we need. So of course, the remaining requirement will be the moment of inertia about the centroidal x-axis. If you recall in our integration, it will only be solved using the transfer formula. Okay, so in the composite method, we had to solve, or we were going to use the transfer formula or the parallel axis theorem twice. Okay, so let me go back with the formula for the transfer. This is the formula on what we intend to solve. So it's Ixx minus the area times y bar squared. So in composite, this becomes summation of the Ixx, okay? And this becomes summation of the product of, uh, sorry, this is summation of the area. Yes, it's correct. Summation of the area and the y bar squared. So we are going to use this transfer formula or parallel x theorem to solve for ices of x, meaning this is the first step, or this is the first, or this is the last. This is the last time that we'll be using the transfer formula or the parallel axis theorem. The first time is to solve for the summation of ixx. So for the summation of ixx, to solve this, we will need the summation of ic sub x plus summation of the product of the area in y squared. So you have to remember that we divide the whole or original area into parts. So the data that we have in each column and each row will be the data for each part. Then when we add them, that is coming from parts to whole, no? So the IC sub x in here is different from the IC sub x that we are trying to solve. The summation of IC sub x is the sum of the moment of inertia about the centroidal axis of each part. While the summation of, the item sub x that we intend to solve is the moment of inertia about the centroidal x-axis of the entire figure. No? Uh, that is before we divide it into parts, the entire figure. So they are different. So based on the formulas that we need to use, we already have the summation of, well, need the y squared. So that's the next step, no? Solve for y squared. We already have the values of y in the second column. So we just need to get the square of this. Okay, so let me use the calculator. The first is square of 3.5, or basically multiplying 3.5 and 3.5. Okay, so that will be 12.25. So that's 12.25. So this is 12.25. This is 12.25. Square of 1, of course, that's the square. The sixth column, since we will need the product of the area and y squared, we multiply second column to the fifth column. So units becomes into the fourth. Okay. So basically that's 3 times 12.25. Calculator again. We have 3 times 12. Sorry. Uh, so we have 3 times 12, 12.25. We get 36.75. So 36.75. Same. 36.75. 12 times 1, that's 12. Then we add all of that. So that's 36.75. So it's like multiplying 2, 73.5 plus 12. We will get 85.5. So this is 85.5. So the last is the summation of IC sub x. So that will be our seventh column. So the IC sub x is the application of the formula that we solve or derive or prove in a in a rectangular element. So remember in our discussion, regardless where I solve the area. So whether in different rooms and the moment of inertia about the centroidal x or centroidal y, uh, using the same dimension will give you the same results. What will be different will be their moment arms, right? So if I draw the figure in room one, if you're in room two, so you will have a further distance, no? But the area, the moment of inertia about centroidal x and y, they are all the same. So I mean to say, remember when we use we have proven the formula of the moment of inertia about the x of any given rectangle to be equal to bh cube over 12. So that will be that's what we'll be using, no? So base being for the first element, the base is this, which is 1, the height is 3. So we apply the formula. So that should be, okay, 1, sorry, now 1 times 3. So we have cube. How do I represent it? So just 3 times multiplying 3. Okay. So 3 times multiplying 3, then divided by 12, I will get 2.25. So that's the one that I'm going to write for both parts. 2.25. So for the the bottom part or part 3, base is 6, height is 2. So we make use of the formula. Calculator, base is 6 times the height is 2 cube. So we multiply 2 3 times. Then we divide it by 12. We will get 4. So this is 4. We add them, summation of I c sub x, we will get 8.5 or 8.50. So for the first time that we're going to use the transfer formula, that is for the solution of this ixx. So for summation of ixx, so summation of ixx is equal to summation of ic sub x, oh sorry, which is 8.5. Unit is inch to the fourth plus summation of the product of the area and y squared. So that's the 85.5 inch to the fourth. Add. So let's use for the calculator again. So we have 8.5 plus 85.5 then equals 94. Okay. So this is equal to 94 inch to the fourth power. Now, for the second time that we're going to use the transfer formula, that is for the required moment of inertia about the centroidal x, which this is the formula. So the ic sub x equal to summation of ixx, which we already solved to be equal to 94 inch to the fourth minus the total area is 18 square inch and the computed centroid or y bar is 1.83 above the x-axis square. Okay, so let's solve. 94 minus 18 times 1.8 squared. So we have 94 minus 18 times 1.83 squared close 33.72. So the answer is 33.72 inch to the fourth power. So that is our uh, final answer for the required of this problem. So what was required? What is the y bar? That is 1.83 above the x-axis. And what is the moment of inertia of the area of this above about the centroidal x-axis? So that's the axis of x equal to 33.72 inch to fourth. Okay. So the last part is an alternative solution that I'll be using to solve this one. Okay. But which will be applicable if you will be answering cross sections or section properties which are hollowed. Okay. Or I mean areas which are hollowed. What will happen to the solution of the centroid? What will happen to the solution of the composite inertia about the centroidal x or y-axis? No? So solving this problem using that alternative solution will definitely can be used when you're solving hollowed areas. Okay. So how do I do that? So let me check. Use again figure. So let me just snip this after though. This is the entire figure, but I'm going to snip this again. I'm going to use this. Okay. And I'm going to clear the frame. So I'll be using this figure and I will write here alternative solution. Alternative. So for our alternative solution, like I said, the reason why I'm showing this is whatever you will learn from this solution, it will be applicable on how you solve hollow areas. Okay. So instead of dividing this figure into three parts, I'm going to divide this into two parts only. Okay, so you heard me, no? I'll be dividing it into two parts. I have extra shapes here. Let me use this. So the first part will be this one, and the second part, sorry, is this one. So I'll be having two rectangles. Okay, so that's two rectangles. So this is the x-axis. This is also the x. Remember, there's a gap which is 2 inches. This is my first part. This is the second. So the making a solid rectangle, then subtract the smaller rectangle will give me this figure. So in the first figure, solid rectangle, the larger rectangle, I have 6 inches and 5 inches. For the smaller, I have so minus 6 minus 2, so 4, and the height is 3. So if I do the parts, the column 1 parts, I only need to consider two parts. So the area per inch. First part, 6 times 5, so that is 30. Second part is 4 times 3, 12. But since you're going to subtract the area, that should be minus. So if you solve for the total area, you will still get 18. Similar in what we had on the earlier method, no? Column 3 is the height of the centroid of each part above the reference axis. Okay? So part 1, since it's already on top of the x, I just simply divide by 5 by 2. That will be 2.5. And this one, I divide the 3 inches by 2. So that's 1.5 plus the 2 inches, which is the gap. So basically, this is 3.5. Fourth column is product of the second and the third. Okay. So that will be cubic inch. So first is 30 times 2.5. 2.5 times 3 is 4.5. Then times 0 is 45. But let's just check that here. 30 times 2.5. That is 75. Sorry. It should be 75. So this is 75. Next one, we have negative 12 times 3.5. So we have 12 times 3.5. So negative means to say we will have negative 40. We get the total. So 75 minus 42, that is 33. So remember, when you solve for the y bar, uh, we have the same 33-inch cube over 18-inch squared. We will get 1.83 inches also. Okay, same centroid. Fifth square of the y, so that's 2.5 square. So 2.5 square, 6.25. So this is 6.25. The other one is 3.5 square. So 3.5 square, that's 12.25. 12.25. Then for the 6, we'll multiply the area and the y squared. So the unit becomes inch to the fourth. First is 30 times 6.25. 30 times 6.25. So that is 187.5. 187.5. Then we have 12 or negative 12. Negative 12 negative times 12.25. You will get negative 147. So we have negative 147. We solve, uh, this is 40.5. 40.5. Okay. Last will be the IC sub x of each rectangular parts. And this one, of course, same formula. We use pH cube over 12. So for the first part, we have uh, 6 times 5 cube. So how is cube? 5, 3. You get 7, sorry, divided by 12, you will get 16.5. And smaller rectangle, 4 by 3. No? So we have 4 times 3 cube, and over 12, that is 9. Since we're going to remove the part, it should be negative 9. Then you get summation of I sub x. So that's 2.5 minus 9 equals 53.5. Okay? So this is 53.5. So for the first transfer formula, we use summation of x, sum of the IC sub x, plus the summation of the area and y squared, 40.5. So 0.5 is zero point 0.1, 3 plus 1, 0 plus 1 is 4. So we will get 94. So I think at this point we get the same. No? In the first solution, summation of I is also 94. So in my solution, I mean in this alternative solution, I also got 94 in the board. So definitely, since I have the same area, same y bar, same summation of ix, I'll be getting the same moment of inertia about sinusoidal x-axis. Okay? So you follow the formula, you will get the same. So that should be our example. So it's a little bit longer, so let me stop my presentation. You just need to watch this so that you will know uh, the composite method and compare it with the integration method. Okay, so let's stop this. Okay, I will record this one. Let me just stop the recording. Stop recording.